So in the previous lecture, we were discussing method of undetermined coefficient, method of undetermined coefficients for solving higher order linear non-homogeneous ODEs with constant coefficients. I have solved a couple of examples here on the board. Today, we are going to discuss a situation where this method fails. You can say that it is a glitch in this method. In this method, you can say. Means there is an error or in one situation, this method fails. We are going to discuss what is that situation. For example, let's discuss this with the help of example. For example, if we have y double dash minus 5y dash plus 4y is equal to 8 e raised power 4x. 8 e raised power 4x. Now, in order to solve this differential equation, what we do usually, we try to find the complementary solution and then particular solution. Sorry. How do we find complementary solution? We write the associated homogeneous differential equation, which is associated to this differential equation. So we can write here corresponding homogeneous ODE is what? It is y double dash minus 5y dash plus 4y is equal to 0. And in order to solve this, what we do, we write the characteristic equation. Characteristic equation, how do we write it? First, we write this differential equation in this form, d square minus 5d plus 4 times y is equal to 0. And then we write characteristic equation by looking at the d. So it is m square minus 5m plus 4 is equal to 0. Now we try to find the roots of this equation. Now, we can factorize this polynomial, characteristic polynomial equation, and we can write m square minus 4m minus m plus 4 equal to 0. So from here, what we obtain, it is m minus, let me see that. So we can write m minus 4 into m minus 1 is equal to 0. So the roots are m is equal to 1 and 4. Now you can see that the roots are real and distinct. So we can write the general solution. The roots are real and distinct. Therefore, the general solution or the complementary function, complementary solution kindly mute your mics. So complementary solution is what? It is yc denoted by yc, and it is, we have real and distinct roots. So we can write c1 e raised power 1x plus c2 e raised power 4x. So this is our complementary solution. Now what? Now we are going to find the particular solution of this differential equation, which is given. In order to find the particular solution of this differential equation, what we do, we look at the form of the right-hand side function, g of x. Now, The right hand side is basically exponential function e raised power 4x. Now, according to the rules which we have discussed in the previous lecture, how can we guess the particular solution? Okay. Now, we assume yp of x is equal to a times e raised power 4x. According to the rules which we have discussed in the previous lecture, the what we assume, or you can say that the particular solution, guess of the particular solution is of this form. Now, if we insert this solution, what we have to do here, we have to find the value of unknown constant a, which is undetermined coefficient of the particular solution. This is what method basically tells us how to implement this method. Yp is equal to a times e raised power 4x. Now, what we do in order to find this constant a, we insert sorry, this yp in the given ODE. Okay, if we insert it in the given ODE, what we obtain, yp double dash yp dash plus 4yp is equal to 8 times 4x, e raised power 4x. Now, what is yp? Its double derivative is 16a e raised power 4x minus 5 times first derivative. It is 4a e raised power 4x and plus 4 times a e raised power 4x is equal to 8 e raised power 4x. Now, taking common e raised power 4x, what we obtain, 16a minus 20, 5 or 20, and 4a. So it is 16a minus 20a plus 4a is equal to 8 e raised power 4x. Now, you can see that this term is 0. This is 0 because 16a plus 4a is 20a, and we have again minus 20a. So we obtain 0 is equal to 8 e raised power 4x, which is not possible. If we obtain this kind of expression, it is not possible. And we are unable to find that, that unknown constant a if we assume the y particular of this form. Now, here the method fails. This method does not give us the value of the coefficient a. Is there a question in the chat window? At what time the quiz will occur? 12:50, yes. Now, this method fails. Now, in this situation, what we do and why did this method fail here? The assumed particular solution is this one, a e raised power 4x. Now, if we look at closely at the complementary solution is what? It is yc c1 e raised power x plus c2 e raised power 4x. Okay. Now, look at sorry. Look at closely at the complementary function and the assumed particular solution, assumed. You can see that here, this term c2 e raised power 4x, and what we are assuming here, a e raised power 4x, where a is arbitrary constant, and in complementary solution, c2 is again an arbitrary constant. If they are both equal, C2 is arbitrary constant, A is arbitrary constant, they can have any value. If they are equal. Okay, if C2 is equal to A, if C2 is equal to A, then this particular solution which we have assumed is already there in the complementary function. Okay, this assumed particular solution is already present in the complementary solution. So these two solutions, Y, C, and this, they're not linearly independent solutions. Y particular solution, YP, depends on basically the function which is already there in the complementary function. That is why this method fails. So in this situation, when the assumed particular solution is already present in the complementary function, this method will always fail. Now, what to do in this situation? In this situation, we always, now what to do in this situation? In this situation, we always multiply the assumed particular solution, whatever it is, by x power n, where n is an integer, where n is positive integer. N is positive integer, and we choose the value of n in a way such that, or you can say that we choose the value of n in a way, or smallest possible value of n, smallest possible value. In a way such that the repetition in the particular solution and the complementary function, it disappears. Okay, the repetition. Now, the complementary function, sorry, particular solution was a e raised power 4x. If we choose n is equal to 1, okay, if we choose n is equal to 1 here, then we are assuming now yp is equal to a times x e raised power 4x. Now, you can see that this solution is not present in the complementary function, which we have already calculated. So this solution, this assumed solution, is now different from the solutions which are already present in the complementary function. What was complementary function? It was yc is equal to c e raised power c1 e raised power x plus c2 e raised power 4x. Now, e raised power 4x is a different function, and x e raised power 4x is a different function. Okay, they are linearly independent. They do not depend on each other. We cannot obtain one function from the other function. So now we can see that this particular solution, assumed particular solution, is different from all the functions in complementary solution. This is how we eliminate this glitch in this problem. This, you can say, in this situation, the method will not fail. But remember that if the assumed particular solution is already present in any term of the complementary solution, then this method will fail. And what we do in this situation, we multiply that complementary assumed particular solution by x power n, and we choose the value of n, minimum value of n, so that the repetition of particular integral, particular solution is basically it eliminates from the complementary solution. Okay, so that it is not present in the complementary solution. I hope you get it. If you have any question, you can ask me. Now we do again the similar procedure. What we do now, we insert this function into the given differential equation and solve for a. Then we would be able to find the constant a. Okay, now we are going to repeat this procedure. This one, we are going to put again yp, the updated one. Here, now yp was basically, yp now, the new yp is ax e raised power 4x. Now yp dash, we need yp dash in order to put it there, so we need to calculate it separately. A times x e raised power 4x times 4, so we put 4 here, plus a x ka derivative 1 e raised power 4x. Okay, we can write this thing as a times e raised power 4x times 4x plus 1. Okay, now we can calculate similarly yp double dash of x, which is, we'll apply the product rule here, and it will be, if we take the derivative of this term first, the derivative is 4, so we obtain 4a e raised power 4x plus this whole term, 4x plus 1 into a, and the derivative of e raised power 4x is e raised power 4x times 4. So we put 4 here. So this is your second derivative now. We put all these values in the given differential equation here. What we obtain, 4a e raised power 4x plus 4a times 4x plus 1 e raised power 4x minus 5 times the first derivative. First derivative is a times e raised power 4x times 4x plus 1 plus 4a, this one, yp 4ax e raised power 4x is equal to 8 e raised power 4x. Now, simplifying this thing and comparing the coefficients of e raised power 4x on both sides, we obtain a is equal to, 8 by 3. We obtain a is equal to 8 by 3. Therefore, our particular solution is what? Our particular solution is, it is 8 by 3 x e raised power 4x. And finally, we can write the general solution as y of x is equal to yc of x plus yp of x, means complementary solution plus particular solution. So it will be c1 e raised power x plus c2 e raised power 4x plus 8 by 3 x e raised power 4x. So this is our general solution. I hope you get it. If you have any question, you can ask me. Let me show you another example quickly. So let's this one. In the next example, we are going to apply the principle of superposition as well as this glitch in the method. I hope you remember what is principle of superposition. I told you in the previous lecture. Now, for example, we are going to solve this question, solve this differential equation, y double dash plus y double dash plus y is equal to 4x plus 10. 4x plus 10 sine x. We need to solve this differential equation, this non-homogeneous differential equation with constant coefficient. You can see here that the right-hand side is sum of two different types of functions. The right-hand side is sum of two different type of functions because this function is a polynomial function of degree 1. Okay, degree 1. And this is what? It is a trigonometric function. So we can use principle of superposition here. Either we can solve two different differential equations. For example, we can say that we can split this differential equation into two differential equations. For example, we can write y double dash plus y is equal to 4x and y double dash plus y is equal to 10 sine x. So this is our first differential equation and this is our second differential equation. We can solve these two differential equations separately, but remember that the left-hand side is same. So the complementary solution for both these differential equations will be same. Okay, complementary solution will be same for these two differential equations because the left-hand side is same and complementary solution is a solution of the associated homogeneous differential equation. Okay. What will be different in these two differential equations? The particular solution in this differential equation will be different from the particular solution in this differential equation. Okay, we can find particular solutions separately for these two differential equations, and then at the end we can add those two particular solutions to get a particular solution of the given differential equation. This is what principle of superposition is. Okay, the complementary solution will be same for these two equations, and we write the associated homogeneous differential equation in this way, and we can find the characteristic equation this, and then the roots of this characteristic equation is r m square minus 1, and the roots are m is equal to plus minus iota. Okay, you can write it 0 plus minus iota. So the complementary solution for this homogeneous differential equation will be what? It is yc of x is equal to c1 cosine of x plus c2 sine of x. Because here we have 0, so e raised power 0 will be 1. So this is your complementary solution. Now, let's come towards the particular solution. Particular solution of the given differential equation will be the sum of particular solutions of this and this differential equation. So in general, particular solution of the given differential equation is the sum of particular solution, first particular solution of the first differential equation and the particular solution of the second differential equation, this one. Now, what will be P1? How can we assume it? We know that the right-hand side function is a polynomial function of degree 1. So how can we assume P1? Why P1 of x will be a times x plus b. Because the right-hand side function is a polynomial function of degree 1. And the second particular solution is what? Now, we look at the right-hand side of the second differential equation. It is 10 sine of x. So according to the rules which we have discussed in the previous lecture, the assumed particular solution in this case will be, we have already written a and b. So you can write here maybe e cosine of x plus f sine of x. So this will be the assumed particular solution in the second case. Okay, but remember that in this second particular solution, we have a term here, f sine x. F sine x, this term is already present in the complementary solution here. because the constants are arbitrary, and it doesn't matter whatever the value of constant, we look at the function only. Now, in the second particular solution, you can see that f sine of x, and here you have c2 sine of x. So this term of this assumed particular solution is already present in the complementary solution. So what we do here, we again apply the similar kind of rule. We multiply this second yp by x power n and choose the value of n, minimum value of n, so that all the terms in the assumed particular solution are different from all the terms in the complementary solution. So in this case, I'm going to choose here e raised power, x, because if we choose the value of n is equal to 1, it will make the two functions different. So I'm going to choose the value of n is equal to 1. So the new complementary solution in this case will become now this thing. I hope you can see it and you get it. Why do we multiply here x power n? Just to make different these functions from the functions which are already complementary, which are already present in the complementary solution. Okay, and this one also, cos x is also present here. Sin x is also present here. Okay, now we multiply this assumed particular solution by x just to make different these two functions from the complementary solution. Now we do again, we would do the same in order to find the constant. There's no problem with the first particular solution. The problem is with the second particular solution. So we multiply only the second particular solution by x. Now we can solve these two differential equations separately, and we can find first particular solution and then second particular solution. And then the particular solution of the given differential equation will be sum of yp1 and yp2. And then we can write the general solution, which is the sum of complementary solution and then particular solution. I hope you get it, and you can do it yourself. If you have any problem, if you have any question, you can ask me. I give you maybe a couple of minutes. You try to solve it, and I wait for your solution. Now we are going to discuss the applications of, let me change the view, this one. Now we are going to discuss the application of second order differential equations with constant coefficients, whether they are homogeneous or non-homogeneous. And the first application which we are going to discuss is the spring mass systems. Spring mass systems are basically the systems where a spring, for example, you can say that a spring is attached to a rigid wall, or you can say that this spring is hanging and it is attached to this, it is fixed with this fixed or rigid wall. Now, if we attach a mass an object or anything of mass m to this free end of the spring. Okay, this is basically unstretched spring. It is only hanging. Its one end is hanging with the wall, and the other end is free. Okay, this is basically you can say that the original spring, or you can say it is unstretched spring. If we attach a mass m to the free end of this spring, it will definitely, because this mass would have weight, which is the gravitational force acting on this mass. So definitely there is a weight of this mass, and there must be some extension in this spring. So the original, if the original length is L of this spring, then there must be some extension in the length of this spring. So this is the extension, and this extension or elongation of the spring is basically what? It is denoted by S. Okay. So this is basically the extension in the spring. Now, when we attach a mass to this spring, there are two forces acting on this mass. One is basically the weight of this mass, which is basically a gravitational force, and the other one is the restoring force, which we denoted by Fs. Because the spring, it basically try to return back to its original position. So there must be a restoring force. Now, the Hooke's law, Hooke's told us that in the absence of any other force, acting or imposing on this system, because there must be some other forces which may be imposed on this mass, but we are ignoring those forces. Then the Hooke told us that these two forces must be equal. W is equal to Fs. The weight force and the restoring force must be same. What is the weight force? It is usually mg, where m is the mass of the body or whatever thing is this object, and g is the gravitational acceleration. And what is this Fs? He told us that Fs, which is the restoring force, and it is going against the motion or against this weight force, then it must be negative k times s, where what is k? K is some proportionality constant. That is Fs is what? It is proportional to s. And if we eliminate this proportionality sign, we can write it in this form, k times s. This restoring force is always, it is what? This force is proportional to the extension, this extension in the length of a string. And this force is basically opposite to this weight force. Then always we put here a negative sign. Fs is equal to minus k times s. Okay, this is basically what? This is the Hooke's law. We use this law in order to derive second order differential equations. Now, this spring mass system, in this situation, when the mass is in the equilibrium situation, equilibrium position, that it's not moving up and down, then there are two forces acting on it, the weight force and restoring force. They must be equal when this mass is in equilibrium position. This mass is not moving. You can say that it is in equilibrium position. It is not moving. Then we have this rule or this law, and we can write that mg plus k times s is equal to 0. Now, remember this equation. We will use this equation further in order to derive the differential equation. This is what we call it Hooke's law. Now, in a third situation, when we should I extend it? When we hold this mass and we pull it downward or upward and leave it, then this mass will start oscillating here. It will start moving. Okay. In that situation, we can model the differential equation. We can model the motion of this mass, the true to and fro motion, because when we hold it, pull it down or upward and leave it, then this mass will start oscillating here due to the spring. And this motion, we can model it by using some physical laws. For example, Hooke's law and the second law of Newton's second law of motion. So for example, if we pull this mass downward by an extension and by a further extension of this spring, when we hold it and pull it down, there will be further extension in this string. Okay, we assume that further extension is x. If that further extension is x, and we after extending this mass or pulling this mass, when we leave, this will start moving, and that motion can be modeled by using Newton's second law. Now, what is Newton's second law? It tells us, and we call it, I hope you know what is Newton's second. You know what is Newton's second law? Second law. It is what? It is that sum of all forces acting on a body which is moving is equal to m times its acceleration. Okay. Now, how many forces are basically there acting on this mass when we pull it and leave it? And this mass start oscillating here. It will be in motion, and we are assuming that there are only two forces which are acting on this spring mass system. One is the restoring force and the other is weight force. So we can say here that sum of forces, one is the weight force plus the second is the restoring force. This must be equal to m times a. Okay. If we assume that, let x of t denotes the position of mass m, which is moving at any time t. Now, this is how we are going to use this Newton's second law. Now, I told you that we pull this mass downward or upward and leave it. Then this mass will start oscillating here. It will start moving. Okay. When we pull it down, there must be some further extension in the length of the string. Now here, in this situation, the restoring force, which was what? It was minus Ks. Now, if there are some further extension here, then the restoring force must be what? It is minus K times S and minus K times X. Or you can simply say that minus K times X, S plus X, because now the extension is XS plus X. S extension is due to the mass of that object, and X is the extension. It is due to the pull, which we have pulled that mass downward or upward in order to put this mass in a motion. Okay. Now, in this situation, weight is mg minus, because Fs is what? It is minus K times S plus X is equal to m times A. A is what? Acceleration of that moving mass. Then we can extend the acceleration as d square x by dt square, because x is basically it denotes the position of the mass m at any time t. Now we can assume here that the mass, when we pulled it, it started moving from the equilibrium or the rest position. Then we can say that mg minus ks and minus k times x is equal to what, m d square x by dt square. ठीक है, यहाँ पे we told here that f is minus k s. आप यहाँ पे कह सकते हैं कि mg is equal to ks, not minus. We will take the absolute value here because the forces will be equal. The amount of the force will be equal. They will not be negative here. So there will not be negative here, and we must have a negative sign here in this equation. So now by using, the force will be negative, but the magnitude of these two forces will be same. Okay. Now using this equation, we can put that thing here, this one equal to 0. And what we have obtained here, we have obtained m d square x by dt square minus kx is equal to minus kx. And further, we can write m d square x by dt square plus k times x is equal to 0. Okay. So this is the differential equation which we have obtained for this spring mass system. For this one, when we are assuming that there are only two forces acting on this object, one is the restoring force and the second is the gravitational force, the weight force. Okay. And when we pull this mass downward or upward to start the motion of this mass, then that motion can be modeled by using this differential equation. And it is what m is a constant, d square x by dt square plus k times x, where k is a constant. This k is called a spring constant. Spring constant, basically, it depends on the properties of the material of the spring, how stiff that spring is. Okay? It depends on its value depends on that stiffness of the spring. There are other things which are involved in this value of k, but you can remember that mainly the value of k depends on the stiffness of any particular spring. Now, the natural initial conditions which we can put in this situation, because it's a second order differential equation, we also need a couple of two initial conditions in order to find the unknown arbitrary constant in that problem. Now, the first condition which we can put here on the displacement x of 0 is equal to some x naught, and the second condition on the velocity at time 0 is equal to x1, for example. Now, the problem along with these two initial conditions, what is the problem? M d square x by dt square plus k times x is equal to 0. So now this whole problem represents the motion of the mass in this spring mass system. When we are assuming there are only two forces acting on this motion of this mass, one is the restoring force and other is the weight force. This kind of motion, we call it free undamped.
सर
जी बेटा.
क्विज का टाइम शुरू हो गया और वो अपलोड भी हो गया, so can we start?
Just give me 1 minute.
Okay.
So this motion of that spring mass system, which gives us this model, and this model can be solved in order to find the position of that mass at any time t. That is, we need to solve this differential equation along with these two initial conditions, and we can obtain the value of x of t, which basically gives us the position of that mass at any time t. So this kind of motion is called free undamped motion. Undamped means there is no friction or resistive forces, which we are assuming that there are no resistive forces or frictional forces which are trying to slow down the motion of this mass. When we pull it down or upward and leave it, it will start moving. If there are no friction forces, it will oscillate always. It will not stop. So there will be oscillations, permanent kind of oscillations. The oscillations will not stop. The motion will not stop for forever. So this is called free undamped motion. If in the next problem we shall assume that there are some frictional forces which slow down the motion of that mass, and that kind of situation will be called free damped motion. And further, some other cases of the similar kind of motion. We'll try to solve this model in the next lecture and find the value of xt, and we'll discuss some different situations. I hope you understand. If you have any question, you can ask me.